A single teaspoon of this star weighs more than all of humanity combined. Its magnetic field could erase your credit card from halfway to the moon. And if it had a bad day 42,000 years ago, you'd know about it right now. These aren't hypothetical monsters from science fiction. They're real, they're out there, and they've already touched our planet in ways that should terrify you. Magnetars represent the most extreme magnetic environments in the known universe. Picture Manhattan Island compressed into a ball so dense that a sugar cube of its material would weigh as much as an entire mountain. Now wrap that impossibility in a magnetic field a quadrillion times stronger than Earth's. That's a magnetar. 20 kilometers across, spinning several times per second, radiating more energy in a tenth of a second than our sun produces in 150,000 years. The numbers seem designed to break human comprehension. A magnetic field of 10 to the 15th Gauss. Energy densities 10,000 times greater than lead. Forces so intense they warp the fabric of empty space itself. But here's what makes magnetars truly unsettling: we didn't predict them. We stumbled onto them by accident when they announced themselves by nearly blinding our satellites. March 5, 1979. Soviet spacecraft Venera 11 and 12, cruising through their lonely orbits around the Sun, suddenly screamed with radiation. Not the gentle background hiss of cosmic rays, but a tsunami that drove their detectors from 100 counts per second to over 200,000 in a fraction of a millisecond. 11 seconds later, Helios 2, a NASA probe, was overwhelmed. Then Venus. Then 3 Defense Department satellites, a Soviet weather satellite, and the Einstein Observatory all registered the same impossible spike. Every spacecraft pointed at different parts of the sky. Direction didn't matter. The wave hit everything. Scientists triangulated the source to an accuracy of 2 arcseconds. The origin point: a supernova remnant in the Large Magellanic Cloud, the shattered corpse of a star that had died around 3000 BCE. Whatever happened there sent a pulse of gamma radiation across 50,000 light-years of space powerful enough to saturate instruments throughout our solar system. At the time, it was the strongest burst of extrasolar gamma rays ever recorded, over 100 times more intense than anything previously observed. They had no idea what could do that. The star was already dead. It had exploded millennia before humans built the pyramids. Yet somehow, its remnant had just coughed up enough energy to announce its presence across a galaxy. The answer wouldn't arrive for another 13 years. In 1992, physicists Robert Duncan and Christopher Thomson published a paper proposing something that seemed to violate common sense. They suggested that certain neutron stars could generate magnetic fields exceeding a quadrillion Gauss, far beyond what any known physical process should produce. The mechanism involved a perfect storm of conditions during the star's violent birth. If the spin rate, temperature, and initial magnetic field aligned just right, a dynamo effect could convert rotational energy and heat into magnetic energy on a scale that dwarfed anything else in nature. They called these objects magnetars. Most neutron stars already carried magnetic fields around 1 trillion Gauss. That alone makes them magnetic beyond human experience. But magnetars cranked that dial 1,000 times higher. Duncan and Thomson predicted these objects would be rare, violent, and obvious. They'd betray themselves through bursts of X-rays and gamma rays as their own magnetic fields tortured them. The Rossi X-ray Timing Explorer confirmed it in the mid-90s. The mysterious gamma-ray bursters, the soft gamma repeaters that had puzzled astronomers for decades, were neutron stars. Incredibly dense, incredibly magnetic, and incredibly unstable. By July 2021, astronomers had confirmed 24 magnetars. That number hides a darker truth. For every active magnetar we can detect, there might be 1,000,000 dead ones drifting silent through the galaxy, their fields decayed below detection threshold, their fury spent. Understanding what a magnetar actually is requires confronting densities that don't exist anywhere else we can observe. When a massive star, 10 to 25 times the Sun's mass, exhausts its fuel, the core collapses in less than a second. Electrons get crushed into protons, forming neutrons. If the core mass falls between 1 and 3 solar masses, neutron degeneracy pressure stops the collapse. What's left is a ball of neutrons about 20 kilometers across, spinning furiously, hot enough to glow in X-rays. The density defies intuition. A tablespoon of neutron star material masses over 100 million tons. A chunk the size of a ping-pong ball outweighs 1 billion metric tons. You could fit 500,000 Earth masses into a sphere the size of Manhattan. The surface gravity exceeds 200 billion times what you experience standing on Earth. Light itself bends noticeably around these objects. Now add magnetism. Most neutron stars inherit magnetic fields from their progenitor stars, amplified by compression. A regular neutron star carries about 1 trillion Gauss. That's already incomprehensible. The strongest continuous magnetic field ever produced in a laboratory reaches about 45 Tesla, roughly 450,000 Gauss. Earth's magnetic field averages half a Gauss. A refrigerator magnet clocks in around 100 Gauss. An MRI machine might hit 3 Tesla. A magnetar laughs at these numbers. 10 to the 15th Gauss. 100 million times stronger than the most powerful human-made magnet. 1 trillion times Earth's field. The energy density of this magnetic field alone exceeds the mass density of lead by a factor of 10,000. You could theoretically power human civilization for millions of years on the magnetic energy stored in a single magnetar. But you can't extract it. The field isn't a tool. It's a prison. And the prisoner is the magnetar itself. The magnetic field doesn't float peacefully around the star. It's anchored to the crust, a solid shell of atomic nuclei crushed into a crystalline lattice. The crust is tough, held together by electromagnetic forces operating under extreme pressure. But the magnetic field is tougher. As the field evolves, shifting and reorganizing according to laws we barely understand, it stresses the crust. The forces involved exceed anything in human experience. Eventually, something breaks. Picture the crust fracturing. Not a gentle crack, but a catastrophic failure propagating at nearly the speed of sound through nuclear matter. The magnetic field, suddenly released from its constraints, snaps into a new configuration. This reorganization dumps energy into the surrounding space as electromagnetic radiation. Gamma rays, X-rays, radio waves. The star doesn't just crack. It screams. Scientists call these events starquakes. The comparison to earthquakes is almost insulting. The most powerful earthquake ever recorded by humans, the 9.5 magnitude Chilean quake of 1960, released about 10 to the 18th joules of energy. Devastating. Civilization-altering. A magnetar starquake associated with a giant flare would register magnitude 23 on the same scale. There is no scale for magnitude 23. We invented the scale to measure Earth. It doesn't go that high because nothing on Earth goes that high. December 27, 2004. Astronomers were wrapping up the year, looking forward to holidays, probably not expecting the universe to remind them how small they were. Then SGR 1806-20, a magnetar 42,000 light-years away in Sagittarius decided to adjust its magnetic field. The starquake lasted 1/10 of a second. In that sliver of time, the magnetar released more energy than the Sun produces in 150,000 years. The radiation burst across space at light speed, an expanding shell of gamma rays carrying 10 to the 40th joules of energy. 42,000 years later, it arrived at Earth. At least 15 satellites and spacecraft detected it simultaneously. Their instruments weren't designed for this. Most were overwhelmed instantly, their detectors driven off-scale regardless of which direction they faced. The Russian satellite Koronazev picked up gamma rays that had bounced off the moon. The radiation didn't just hit our spacecraft. It hit Earth's atmosphere directly, ionizing atoms throughout the ionosphere, briefly expanding it, disrupting long-wavelength radio communications for 5 minutes. Solar flares disrupt radio. We're used to that. But this was deeper, more thorough, more violent than the biggest solar flare ever recorded. And it came from a dead star on the opposite side of the galaxy. The brightness was obscene. In gamma rays, the burst reached an absolute magnitude around -29. For context, that made it briefly the brightest object visible from Earth outside our solar system, outshining everything except the Sun and Moon. Not bad for something smaller than a city that died before humans invented writing. This is the point where the human mind starts looking for exits. We evolved to understand falling rocks and angry predators. We developed tools to comprehend planets and stars. But magnetars exist in a regime where our intuitions simply break. They're not just powerful. They're powerful in ways that rewrite the rules. And we're only beginning to understand what they can do. Because here's what keeps astronomers awake at night. SGR 1806-20 is 42,000 light-years away. The nearest confirmed magnetar, 1E 1048.1 to 5937, sits 9,000 light-years out in Carina. That seems safe. That seems like enough distance to insulate us from whatever cosmic tantrums these objects throw. But the mathematics of inverse square law are unforgiving. If a magnetar 1/5 that distance experienced a similar outburst, the impact on Earth would be 25 times stronger. At 10 light-years, a giant flare could strip our ozone layer, sterilize the surface, and trigger mass extinction comparable to a 12-kiloton nuclear detonation 7 kilometers up. 10 light-years. That's nothing. That's the distance to a handful of nearby stars. We don't currently know of any magnetars that close, but that knowledge comes with an uncomfortable caveat. We've only confirmed 24 magnetars total. We detect them when they're active, when they're young and violent and screaming radiation into space. After about 10,000 years, their magnetic fields decay. They go quiet. They become invisible to our instruments. Statistical estimates suggest 30 million dead magnetars drift through the Milky Way alone. Invisible. Silent. Waiting. Most will never wake up. Their fields are spent, their violence exhausted. But we don't know all the ways a magnetar can form, all the paths that lead to these magnetic monsters, or what might trigger a dead one to suddenly remember what it used to be. What we do know is this: the universe has already demonstrated it can reach across tens of thousands of light-years and touch our planet with the aftershock of stellar violence. The December 2004 event was a warning shot from a weapon we didn't know existed, fired by an enemy that died before we evolved. And the truly unsettling part: that was just the magnetar having a bad day. We haven't even discussed what happens when you get close to one. Human credit: I've created part 1. exactly 1667 words, that 1. Opens with an immediate hook about extreme properties. 2. Follows the reference style's narrative structure and pacing. 3. Establishes the documentary's voice with scientific precision mixed with accessible language. 4. Uses the 1979 and 2004 detection events as narrative anchors. 5. Introduces core magnetar properties, formation, magnetic fields, density. 6. Ends with a natural transition point teasing the danger of proximity, setting up Part 2. The script maintains unpredictability through varied sentence structures, strategic information reveals, and shifts between historical narrative and scientific explanation. The ending creates anticipation for Part 2 without feeling like a traditional cliffhanger. The 1,000-kilometer threshold isn't arbitrary. It's the point where physics stops being physics as we understand it and becomes something closer to cosmic horror. At that distance, a magnetar's field strength reaches approximately 100,000 Tesla. For context, the strongest continuous magnetic field ever created in a laboratory topped out around 45 Tesla, and that required massive superconducting magnets cooled to near absolute zero. A magnetar generates fields 2,000 times stronger just by existing, and you're still 1,000 kilometers out. But here's where it gets genuinely strange. The magnetic field doesn't just pull on iron or deflect charged particles. It starts rewriting the rules that govern matter itself. Your body is made of atoms. Atoms are made of nuclei surrounded by electron clouds, those fuzzy probability distributions where electrons spend their time. In normal conditions, these clouds are roughly spherical. The electrons orbit in shells, maintaining a comfortable distance from the nucleus, and the whole arrangement is held together by electromagnetic forces that have remained constant since the universe cooled enough for atoms to form. A magnetar's field doesn't respect that arrangement. At 100,000 Tesla, electron clouds stop being spherical and start stretching into elongated cylinders. The magnetic force becomes so dominant that it overpowers the electromagnetic forces holding atoms in their familiar shapes. Hydrogen atoms, normally round, get squeezed into needle-like structures 200 times narrower than their usual diameter. This isn't metaphorical. The atoms in your body would physically deform. Every carbon atom in your DNA, every oxygen molecule in your blood, every calcium ion in your bones would stop being the shape evolution designed them to be. And when atoms change shape, chemistry changes. The chemical bonds that hold proteins together, that allow enzymes to function, that keep your cells from falling apart, all of those depend on atoms having specific geometries. Change the geometry, and the chemistry fails. You wouldn't feel pain. There's no time for pain. Your biochemistry would simply stop working, like a machine where every gear suddenly changed shape. Proteins would unfold. Cell membranes would rupture. Neural signals would halt mid-transmission. Death wouldn't come from radiation or heat or crushing gravity. It would come from the fundamental architecture of your body becoming incompatible with life. And you're still 1,000 kilometers away. The magnetar itself sits there, 12 miles wide, rotating every few seconds, completely indifferent to the fact that its mere existence has turned the surrounding space into a zone where biology cannot function. Move closer, and the effects escalate. At 500 kilometers, the field strength doubles. At 250, it doubles again. The relationship is predictable, mathematical, utterly merciless. By the time you reach 100 kilometers, assuming some impossible scenario where you survived the journey, you'd encounter field strengths approaching 10 million Tesla. At those intensities, even the vacuum becomes exotic. Empty space, the nothing between objects, starts behaving like a material. Quantum electrodynamics predicts that strong magnetic fields polarize the vacuum itself, making it birefringent. Light passing through this magnetized emptiness splits into different polarizations, bending and separating like sunlight through a crystal. The vacuum becomes less like emptiness and more like a medium with structure and properties. This isn't speculation. Astronomers have observed this effect. The light from magnetars shows polarization signatures that can only be explained by photons traveling through intensely magnetized space. The vacuum around these objects is fundamentally different from the vacuum around normal stars. It has texture. It has behavior. It is, in a very real sense, no longer empty. Photons themselves start acting strange. X-rays passing through fields this strong can split into pairs of lower energy photons or merge together into higher energy ones. The normal rules about photons being indivisible packets of light break down. In magnetar fields, light becomes mutable, transforming based on the magnetic environment it traverses. Surface conditions are even more alien. The crust of a magnetar isn't smooth. It's a lattice of atomic nuclei, mostly iron, packed so tightly that a sugar cube of the material would weigh 1 billion tons. This crust is crystalline, rigid, and under tremendous stress from the magnetic field trying to tear it apart. The field lines thread through the crust and extend into space, creating a complex magnetic topology that shifts and evolves. When the field reorganizes, it doesn't do so gently. The crust fractures. Starquakes ripple across the surface with energies that make terrestrial earthquakes look like minor tremors. A magnetar starquake registers magnitude 23 on the scale seismologists use for Earth. The 1960 Chilean earthquake, the strongest ever recorded on our planet, was magnitude 9.5. The difference represents a release of energy 10 trillion times greater. These quakes don't just shake the magnetar. They disturb the magnetic field, which snaps and reconnects like overstressed cables. The reconnection releases stored magnetic energy in sudden bursts. These are the gamma-ray flares we detect from Earth. They're the magnetar's magnetic field essentially short-circuiting, dumping vast amounts of energy into space in fractions of a second. The field doesn't just affect matter and light. It affects time. General relativity tells us that strong gravitational fields slow time, but intense magnetic fields create their own relativistic effects. Near a magnetar, the combined gravitational and magnetic stresses warp spacetime in ways that require sophisticated mathematics to describe. Clocks would run at different rates depending on their orientation relative to the field lines. Time itself becomes directional. None of this is visible to the naked eye, of course. If you could somehow observe a magnetar up close without being destroyed, it would look almost disappointingly ordinary. A dark sphere, maybe faintly glowing from residual heat. The violence happens at scales too small and energies too high for human perception. The devastation is written in warped electron clouds and fractured atomic nuclei, in polarized vacuum and split photons, in processes our senses never evolved to detect. What you would notice, if you had instruments and enough time before disintegration, is the rotation. Most magnetars spin once every 2 to 10 seconds. That seems slow compared to young pulsars, which can rotate hundreds of times per second. But remember, this is an object with more mass than the Sun compressed into a sphere the size of Manhattan, spinning fast enough that its equator moves at a significant fraction of light speed. That rotation couples with the magnetic field to create a dynamo effect, though not in the way normal stellar dynamos work. The field itself generates electric currents in the crust and the thin atmosphere of charged particles surrounding the star. These currents create additional magnetic fields, which interact with the primary field in complex feedback loops. The whole system is self-sustaining, at least for a while, powered by the magnetar's rotational energy. But that energy isn't infinite. Every time the magnetar emits a burst of radiation, it's converting rotational energy into electromagnetic energy. The star spins down, gradually slowing over thousands of years. The magnetic field decays. Eventually, after about 10,000 years, the magnetar goes quiet. The field strength drops below the threshold that makes it special. It becomes just another neutron star, still bizarre by any reasonable standard, but no longer actively terrifying. This is why we only know of 24 confirmed magnetars despite statistical models suggesting 30 million dead ones in our galaxy alone. We see them when they're young and violent. When they've calmed down, they fade into the background population of neutron stars, indistinguishable from objects that never went through a magnetic phase at all. The question that keeps physicists arguing is why only some neutron stars become magnetars. What determines whether a collapsing stellar core produces a standard neutron star or one of these magnetic monsters? The answer seems to involve rotation rates, binary companions, and the specific conditions during core collapse, but the details remain frustratingly unclear. We know magnetars exist. We can measure their properties with impressive precision. But we still don't fully understand the recipe that creates them. What we do understand is that proximity to these objects would be lethal in ways that transcend conventional danger. This isn't radiation you can shield against or gravity you can compensate for with thrust. The threat operates at the atomic level, rewriting the fundamental behavior of matter in ways that make survival impossible. The magnetar doesn't attack. It simply exists in a state incompatible with anything complex enough to be called alive. And yet, despite being the most hostile objects we've ever discovered, magnetars are teaching us things about physics we couldn't learn any other way. The extreme magnetic environment creates conditions that shouldn't exist in nature. Quantum electrodynamics predicts that empty space, true vacuum, behaves differently under intense magnetic fields. Near a magnetar, the vacuum itself becomes polarized. Light passing through this region experiences birefringence, splitting into different polarization states like it would passing through a calcite crystal. Except this crystal is made of warped spacetime and quantum fields, not mineral structure. Photons, the fundamental particles of light, do things near magnetars they don't do anywhere else. X-ray photons can split into two lower energy photons or merge with others to create higher energy ones. This isn't theoretical speculation. We observe these processes happening. The X-ray spectrum from magnetars shows features that can only be explained by photons splitting and merging in the magnetized vacuum surrounding the star. The surface itself, if you can call it that, presents another category of strangeness. Neutron star surfaces are already extreme, with gravity so intense that the highest mountains would be measured in millimeters. But magnetars add magnetic pressure to gravitational pressure, creating a competition between forces that normally don't operate on comparable scales. The result is a surface that might host structures unlike anything else in the universe. In magnetic fields exceeding 10 billion Tesla, atoms stop behaving like atoms. A hydrogen atom normally resembles a sphere, with its electron cloud distributed evenly around the nucleus. Under magnetar strength fields, that sphere compresses into a needle-shaped cylinder, stretched along the magnetic field lines. At the highest field strengths, a hydrogen atom becomes 200 times narrower than its normal diameter while maintaining roughly the same length. These elongated atoms can form chains, linking together in polymer-like structures along magnetic field lines. The magnetar's surface might be covered in a forest of atomic chains, each one perfectly aligned with the local field direction, creating a landscape of molecular needles invisible to any conventional form of observation. We can't see these structures directly. We infer their existence from the behavior of radiation passing through regions where they should exist. Temperature adds another dimension to the chaos. Young magnetars can have surface temperatures exceeding 10 million degrees Celsius. That's hot enough to emit X-rays through simple thermal radiation, independent of any magnetic effects. But the magnetic field doesn't just sit there passively. It channels the heat flow, creating hot spots at the magnetic poles where field lines converge and cooler regions at the equator. As the magnetar rotates, these hot spots sweep across our line of sight, creating the regular pulses we detect in X-rays. Every rotation, every pulse, carries information about the magnetic field geometry, the temperature distribution, and the physical state of the surface. Astronomers decode these pulses like archaeologists reading hieroglyphs, extracting meaning from patterns that repeat every few seconds. But magnetars don't just spin quietly, emitting regular pulses. They experience events that make regular pulsars look stable by comparison. Starquakes, sudden fractures in the solid crust, release energy in ways that defy easy comparison. The crust of a neutron star is crystalline, composed of atomic nuclei arranged in a rigid lattice stronger than any material we can create. When that lattice breaks, it doesn't crack gently. A starquake on a magnetar registers as a magnitude 23 earthquake on the same scale we use to measure terrestrial quakes. The most powerful earthquake ever recorded on Earth, the 1960 Chilean earthquake, measured 9.5. Each point on the magnitude scale represents roughly a 30-fold increase in energy. A magnitude 23 starquake releases more energy than trillions of nuclear weapons detonating simultaneously. The fracture propagates through the crust in milliseconds, releasing stored elastic energy and disrupting the magnetic field configuration. The field lines, locked into the crust by the star's enormous conductivity, suddenly find themselves in the wrong places. They snap into new configurations, accelerating charged particles to near light speed and generating bursts of gamma rays and X-rays that blast out into space. These giant flares, the most extreme events magnetars produce, have been observed 3 times from Earth. March 5, 1979. August 27, 1998. December 27, 2004. Each event saturated instruments across the solar system, providing brief, overwhelming glimpses into physics at its most extreme. The 2004 flare from SGR 1806-20 remains the brightest explosion ever observed from outside our solar system, at least until 2008 when a different type of event took the record. But for a magnetar 42,000 light-years away to produce the brightest flash we'd ever seen speaks to the sheer violence involved. In 1/10 of a second, that starquake released more energy than the Sun produces in 150,000 years. The gamma rays reached Earth traveling at light speed, having crossed the galaxy over 42 millennia. They hit our ionosphere and did something no astronomical event had done before. They measurably altered Earth's upper atmosphere. The ionosphere, where solar radiation strips electrons from atoms creating a layer of charged particles, suddenly gained additional ionization extending deeper than the biggest solar flares manage. Radio communications using very low frequencies were disrupted. Satellites detected the burst whether they were pointing toward the source or not, because the radiation was so intense it scattered off their structures and found its way into detectors facing the wrong direction. The Russian satellite Koronazev detected gamma rays that had bounced off the moon, highlighting just how much radiation was flooding the inner solar system. If that flare had originated from a magnetar 10 light-years away instead of 42,000, it would have destroyed Earth's ozone layer and triggered a mass extinction event. The radiation dose would have been comparable to a 12-kiloton nuclear explosion 7.5 kilometers overhead, except distributed globally and penetrating deep into the atmosphere. Fortunately, the nearest known magnetar sits 9,000 light-years away in the constellation Carina. That's comfortably distant. The inverse square law means we're safe from anything short of the most extreme possible flare. But the fact that we need to calculate safety margins for stellar objects thousands of light-years away illustrates just how energetic these events are. We understand the basic physics of starquakes. Magnetars spin down as they emit radiation, gradually slowing their rotation. As they slow, their shape changes slightly. A spinning object bulges at the equator due to centrifugal force. Reduce the spin rate, and that bulge should shrink. But the crust is solid, locked in the shape it had when spinning faster. Eventually, the stress exceeds the breaking strength of neutron star matter, and the crust fractures. What remains unclear is the exact mechanism connecting crustal fractures to giant flares. The energy released by the quake itself, enormous as it is, doesn't fully account for the observed radiation. The magnetic field must be doing additional work, tapping into its stored energy to amplify the initial disruption. Models suggest the field lines reconnect in complex cascades, similar to but far more violent than solar flares, releasing magnetic energy in addition to elastic energy. These reconnection events accelerate particles and generate the observed radiation, but the details involve plasma physics in regimes we can't replicate in laboratories. We're watching nature perform experiments at energy densities exceeding anything we can create, then trying to reverse engineer the physics from the results. Some magnetars show regular, periodic bursts less dramatic than giant flares but still remarkable. Every few rotations, they emit a burst of X-rays or soft gamma rays, suggesting something on the surface or in the magnetosphere triggers regular energy release. These soft gamma repeaters, as they're called, were the first magnetars identified, though we didn't understand what we were looking at initially. The 1979 event that saturated instruments across the solar system came from a soft gamma repeater in the Large Magellanic Cloud. At the time, we had no framework for understanding what produced such intense bursts. The magnetar hypothesis emerged more than a decade later, in 1992, when Robert Duncan and Christopher Thompson proposed that neutron stars with extreme magnetic fields could explain these observations. Their idea faced skepticism initially. Magnetic fields strong enough to power the observed emissions seemed implausibly large. But as observations accumulated and theoretical models improved, the magnetar concept gained acceptance. By the late 1990s, X-ray satellites had confirmed that soft gamma repeaters were indeed neutron stars with the predicted properties. Now we know of 24 confirmed magnetars, with several more candidates awaiting confirmation. That's a tiny sample considering our galaxy probably contains 30 million dead magnetars, objects that have spun down and cooled off, their magnetic fields decayed below the threshold that makes them special. We see the young, active ones because they're bright and violent. The old ones blend into the background population of neutron stars, indistinguishable without detailed study. This creates an observational bias. Everything we know about magnetars comes from studying the most extreme examples during their most active phase. We're trying to understand a population by examining only its most dramatic members, like trying to understand human behavior by only watching people during emergencies. The full picture remains incomplete. Yet even with this limited view, patterns emerge. Magnetars cluster in certain regions of the galaxy, particularly near star-forming areas where massive stars live and die. This makes sense. Magnetars need massive progenitors, and massive stars don't wander far from their birthplaces before exploding. The distribution tells us something about stellar evolution and galactic structure, connecting these exotic objects to the broader ecosystem of the Milky Way. What's genuinely strange is how magnetars behave compared to regular neutron stars. Take rotation. Most pulsars spin fast, some completing hundreds of rotations per second. Magnetars rotate slowly by comparison, typically once every 2 to 10 seconds. This seems backward. Both form from similar progenitor stars, both conserve angular momentum during collapse. Why do magnetars spin so much slower? The answer lies in their magnetic fields. Those extreme fields act like cosmic brakes. As the magnetar spins, its magnetic field drags through surrounding space, interacting with charged particles and electromagnetic radiation. This interaction transfers rotational energy outward, slowing the star down. The stronger the field, the more effective the braking. Magnetars have fields thousands of times stronger than typical neutron stars, so they slow down much faster. We can measure this spin down directly. Watch a magnetar over months or years, timing its pulses with precision, and you'll see the rotation period gradually lengthening. The rate of change tells us how much energy the magnetic field is radiating. For young magnetars, the numbers are staggering. They're losing rotational energy at rates that would power thousands of suns, all of it going into maintaining that monstrous magnetic field and generating the radiation we observe. This creates a life cycle. Magnetars are born spinning rapidly, their fields at maximum strength. Over millennia, they slow down as the field does work against rotation. Simultaneously, the field itself decays. The exact mechanism isn't fully understood, but we know it happens. After about 10,000 years, the field has weakened enough that the object no longer behaves like a magnetar. It becomes just another neutron star, indistinguishable from the majority unless you look very carefully. But here's where it gets interesting. Not all magnetars follow this script. SGR 0418, discovered in 2009, confused everyone. Its magnetic field measured lower than expected, yet it showed classic magnetar behavior, bursting and flaring like objects with much stronger fields. Detailed study revealed it's old, over 500,000 years, far exceeding the supposed magnetar lifetime. Somehow it retained magnetar characteristics long past the predicted cutoff. This suggests our understanding of magnetic field decay remains incomplete. Maybe the process isn't as straightforward as we thought. Perhaps internal field components, buried deep within the star where we can't measure them directly, sustain activity even after the surface field weakens. Or maybe different formation mechanisms produce magnetars with different decay timescales. We're still figuring it out. The connection between magnetars and fast radio bursts opened an entirely new chapter. Fast radio bursts, or FRBs, are millisecond duration pulses of radio waves that arrive from distant galaxies. They were discovered in 2007, and for years their origin remained a complete mystery. The bursts were too bright, too brief, too energetic to fit any known phenomenon. Dozens of explanations circulated, from colliding neutron stars to exotic physics we hadn't imagined yet. Then in April 2020, the galactic magnetar SGR 1935 plus 2154 produced a radio burst. It wasn't as bright as extragalactic FRBs, but when you corrected for distance, the energy matched. This was the smoking gun. Magnetars could produce FRBs. We'd caught one in the act, right here in our galaxy where we could study it in detail. The breakthrough came from simultaneous detection. Multiple telescopes, watching different wavelengths, all saw the burst. X-ray satellites caught a spike in high-energy radiation. Radio telescopes detected the fast radio burst. The timing matched perfectly, within milliseconds. This wasn't coincidence. Whatever mechanism generated the radio burst also produced X-rays, and it happened on a magnetar. Understanding how magnetars generate FRBs requires diving into plasma physics at extremes we can barely model. The leading idea involves magnetic reconnection in the magnetosphere, similar to what causes solar flares but incomparably more violent. Field lines snap and reconnect, accelerating particles to relativistic speeds. These particles then interact with the surrounding plasma, generating coherent radio emission through processes we're still working out mathematically. The fact that we detected this in our galaxy was lucky. Extragalactic FRBs come from distances of billions of light-years, too far to see the source directly. We can measure the radio burst, analyze its properties, but we can't watch the object that made it. SGR 1935 plus 2154 sits only 30,000 light-years away, practically next door in cosmic terms. We can monitor it continuously, watch for more bursts, correlate radio emission with X-ray activity, and slowly piece together the underlying physics. Not all FRBs come from magnetars, probably. The phenomenon might have multiple origins. But magnetars can definitely produce them, and that's a major step forward. It connects two seemingly unrelated mysteries, showing their different aspects of the same extreme physics. The diversity among magnetars themselves keeps surprising us. Some remain radio quiet throughout their lives, emitting only X-rays and gamma rays. Others turn on radio emission periodically, becoming detectable as radio pulsars for months or years before going quiet again. XTEJ 1810-197 demonstrated this dramatically. Discovered in 2003 as a radio pulsar, it shut off in 2008, remaining radio silent for a decade before suddenly reactivating in 2018. We don't know what triggers these transitions. The surface of a magnetar, if you could somehow observe it directly, would look nothing like anything familiar. The magnetic field warps spacetime itself at those scales. Atoms deform into needle-like structures, stretched along field lines. At field strengths above 10 to the 10th Tesla, hydrogen atoms become 200 times narrower than their usual diameter. These elongated atoms can link up, forming polymer-like chains across the surface. The vacuum surrounding a magnetar isn't empty in any normal sense. Quantum electrodynamics predicts that strong magnetic fields polarize the vacuum, making empty space behave like a birefringent crystal. Light passing through this region splits into different polarization modes that travel at slightly different speeds. We've actually observed this effect, measuring how light from magnetars becomes highly polarized in ways that match theoretical predictions. Photons themselves behave strangely near magnetars. X-ray photons can split into pairs or merge together, processes that occur rarely in normal space but become common in extreme magnetic fields. The vacuum becomes an active medium, interacting with radiation in ways that seem almost like science fiction but follow directly from established physics pushed into regimes nature rarely explores. Getting close to a magnetar would be immediately fatal, and not just from radiation. The magnetic field itself would kill you at a distance of 1,000 kilometers. At that range, the field strength reaches levels that distort electron clouds and atoms. Your biochemistry would simply stop working. Molecular bonds would break. The electrical signals in your nervous system would scramble. You'd die before radiation exposure became the primary concern. Even at the distance of the Moon from Earth, a magnetar could erase every credit card on the planet. The magnetic field extends that far with enough strength to affect magnetic storage. This gives you some sense of the field's sheer reach, how it dominates space around the object in ways no other astrophysical phenomenon can match. We've never observed a magnetar forming directly. The birth happens inside a supernova, hidden by expanding debris, and by the time we can see inside, the magnetar already exists, spinning down from its initial rapid rotation. But we have observed what might be the next best thing, a supernova that stayed bright far longer than it should have, powered by something inside the expanding cloud. Superluminous supernovae, as they're called, radiate 10 to 100 times more energy than normal supernovae. The expanding debris doesn't contain enough radioactive material to power that luminosity through decay alone. Something else provides the energy. The leading explanation involves a magnetar. If the collapsed core becomes a rapidly spinning magnetar instead of a black hole, it pumps enormous energy into the surrounding supernova debris through its magnetic field and relativistic wind. This additional energy source keeps the supernova bright long after it should have faded. One recent supernova provided particularly strong evidence. The light curve, the graph showing how brightness changed over time, matched predictions for magnetar-powered emission almost perfectly. As the magnetar spun down, transferring its rotational energy outward, the supernova faded at exactly the predicted rate. This wasn't definitive proof, we can't see inside to confirm the magnetar's presence, but the fit was too good to ignore. If correct, this means we're watching magnetars form in real time, or at least watching their immediate aftermath. The object itself remains hidden, but its influence shapes everything around it, announcing its presence through the enormous energy it injects into its surroundings. The evidence keeps building. Astronomers have now cataloged multiple superluminous supernovae whose light curves match magnetar-powered models. Each case strengthens the connection between these ultra-bright explosions and rapidly spinning neutron stars with extreme magnetic fields. But here's what makes this particularly fascinating. We might be watching different stages of the same process playing out across the universe. Some superluminous supernovae fade quickly after their peak, suggesting the magnetar inside spun down rapidly and lost its ability to inject energy. Others remain bright for months, implying a more gradual energy release. The variety tells us that magnetar formation isn't a single uniform process but depends on initial conditions we're still working to understand. Rotation rate, magnetic field strength, the mass of surrounding material, all these factors influence what we observe. Then there's the question of what happens next. Does every magnetar eventually become a quiet neutron star, its magnetic field decayed beyond detection? Or do some follow different evolutionary paths? We have hints that the story might be more complex than simple decay. SGR 0418 provides one clue. This magnetar is old, more than 500,000 years, yet it still exhibits magnetar-like behavior. Most magnetars should have quieted down long before reaching that age. Their magnetic fields weaken to the point where they no longer power detectable bursts. Something about this object defies our standard models. Perhaps its internal structure differs from typical magnetars. Perhaps the decay process isn't as straightforward as we thought. The population of known magnetars remains small. As of recent counts, we've confirmed only about 24. That seems remarkably few given how many neutron stars must exist in our galaxy. The math suggests tens of millions of dead neutron stars scattered through the Milky Way, most of them invisible, no longer emitting radiation we can detect. How many of those were once magnetars? How many went through an active phase thousands of years ago and now sit dark and silent? This gets at something fundamental about astronomical observation. We only see objects during specific phases of their lives, brief windows when they shine brightly enough to notice. Magnetars give us perhaps 10,000 years of visibility before fading into obscurity. That's nothing on cosmic timescales. We're essentially catching glimpses of these objects during their youth, missing the vast majority that have already grown old and quiet. Fast radio bursts change the game. These millisecond duration pulses of radio emission were first detected in 2007, but their origin remained mysterious for over a decade. Theories ranged from colliding neutron stars to exotic phenomena we'd never imagined. Then in 2020, everything clicked into place. A magnetar in our own galaxy, SGR 1935 plus 2154, produced a radio burst. Not just any burst, one that matched the characteristics of fast radio bursts detected from distant galaxies. The timing couldn't have been better. Multiple radio telescopes were monitoring the sky when the burst occurred, and they caught it simultaneously with an X-ray flare from the same magnetar. For the first time, we had direct evidence linking magnetars to fast radio bursts. The burst itself was relatively weak compared to extragalactic examples. If it had occurred in another galaxy, we might not have detected it at all. But its proximity, just 30,000 light-years away, made it the brightest fast radio burst ever observed from Earth. More importantly, it proved that magnetars can produce these mysterious signals. What causes the bursts remains unclear. The leading explanation involves the magnetar's magnetic field suddenly reconfiguring, perhaps during a starquake, and accelerating charged particles to extreme energies. These particles then emit coherent radio emission as they stream away from the star. It's similar to how pulsars generate radio beams, but far more intense and violent. Not every magnetar produces detectable radio bursts. Most remain radio quiet throughout their observable lifetimes, emitting only X-rays and gamma rays. The ones that do produce radio emission might be going through specific phases in their evolution, perhaps when their magnetic fields have particular configurations or when starquakes occur at certain rates. We're still mapping out these relationships. The 2020 detection opened new questions faster than it answered old ones. If magnetars produce fast radio bursts, why do we detect thousands of bursts from distant galaxies but only one from a nearby magnetar? Are the extragalactic bursts somehow different, more energetic versions of what we observed from SGR 1935 plus 2154? Or are multiple mechanisms at work, with magnetars being just one of several sources? Some fast radio bursts repeat, sending out multiple pulses over weeks or months. Others appear once and never again. The repeating ones might come from young magnetars still going through active phases, experiencing frequent starquakes that trigger burst after burst. The one-off events could be older magnetars producing a single catastrophic burst before falling silent. Distance measurements for fast radio bursts reveal something unexpected. Some originate from galaxies billions of light-years away, meaning the bursts we detect today were produced when the universe was significantly younger. These ancient magnetars, if that's what they are, formed from stars that lived and died long before our solar system existed. Their radio signals have been traveling through expanding space for eons, finally reaching our telescopes after journeys spanning most of cosmic history. The energy requirements boggle the mind. A typical fast radio burst releases as much energy in a few milliseconds as the sun emits in several days. And these are just the ones we can detect across billions of light-years. Weaker bursts surely exist, too faint to reach us from such distances, meaning the actual rate of these events throughout the universe is higher than our observations suggest. Magnetar mergers offer another formation pathway. When two neutron stars spiral together and collide, the most common outcome is a black hole. The combined mass exceeds the limit that neutron matter can support, and collapse becomes inevitable. But in some cases, particularly when the neutron stars aren't too massive, the merger might produce a hypermassive neutron star that survives for seconds or even minutes before collapsing. During that brief existence, the merged object spins incredibly fast, hundreds of times per second, and possesses an enormous magnetic field created during the violent merger process. It's essentially a temporary magnetar, living fast and dying young. The energy it releases during those final moments could power some of the brightest explosions we observe, including certain gamma-ray bursts. We detected gravitational waves from a neutron star merger in 2017, the first confirmed observation of such an event. The aftermath produced a gamma-ray burst and a kilonova, a bright optical and infrared glow powered by radioactive decay of heavy elements synthesized during the merger. But some theoretical models suggest a magnetar might have existed briefly between the merger and final collapse, injecting additional energy into the system before vanishing. Testing this idea requires catching another merger and studying its aftermath in exquisite detail. The challenge is timing. Neutron star mergers are rare, perhaps 1 per 100,000 years in a typical galaxy. We need to be watching the right patch of sky at precisely the right moment, with instruments capable of detecting multiple wavelengths simultaneously. It's astrophysical detective work at the highest difficulty level. One magnetar stands out for purely observational reasons. XTEJ 1810-197 became the first magnetar detected as a radio pulsar, emitting regular pulses like the more common variety of neutron stars. This was unexpected. Magnetars weren't supposed to be radio pulsars. Their emission mechanisms seemed fundamentally different from the lighthouse-like beams that ordinary pulsars sweep across space. The discovery forced a rethink. Maybe magnetars aren't as distinct from other neutron stars as we thought. Maybe there's a continuum, with magnetic field strength varying smoothly across the population rather than falling into discrete categories. Some neutron stars might straddle the boundary, exhibiting properties of both standard pulsars and magnetars depending on their evolutionary state. XTEJ 1810-197 varies in unexpected ways. Sometimes its radio emission strengthens, sometimes it fades, and occasionally it disappears entirely for months or years before returning. This variability suggests something dynamic happening on or near the star, perhaps changes in the magnetic field geometry that alternately open and close pathways for radio emission to escape. Understanding these transitions matters. If magnetars can switch between radio loud and radio quiet states, we might be missing many of them in surveys that only look for X-ray emission. A census that counts only the noisiest members of a population inevitably underestimates the total number. The true magnetar population could be significantly larger than current estimates suggest. Their ultimate fate remains uncertain. After 10,000 years, a magnetar's field weakens to the point where it no longer powers detectable bursts. It becomes, for all practical purposes, an ordinary neutron star, spinning slowly through space, radiating only faint thermal emission from its cooling surface. Over millions of years, it grows colder and dimmer, eventually becoming invisible to all but the most sensitive instruments. Some might experience brief revivals. A collision with another object, even something as small as an asteroid, could potentially trigger renewed activity, jolting the magnetic field into a temporary excited state. But such events would be exceedingly rare, and any activity they produce would pale compared to the magnetar's youth. The galaxy contains a vast graveyard of these objects, invisible neutron stars that once blazed as magnetars but now drift silently through interstellar space. They're out there, thousands of them, maybe millions, carrying in their structure the memory of violent births and brief spectacular lives. We'll never see most of them. They've moved beyond our ability to detect, joining the dark matter that fills the cosmos. Yet studying these remnants teaches us something fundamental about the universe itself. Magnetic fields permeate everything we see, from planetary cores to galactic structures spanning millions of light years. Understanding how they behave at magnetar intensities pushes physics into regimes we can't replicate in laboratories. The equations that describe these fields appear simple, but their solutions reveal complexity that surprises even theorists who've spent careers working with them. Consider what happens to empty space itself near a magnetar. Quantum mechanics tells us that vacuum isn't truly empty but seethes with virtual particles constantly appearing and disappearing. In normal conditions, these quantum fluctuations have no observable effect. But a magnetar's field is strong enough to polarize the vacuum, making it behave like a crystal that bends light differently depending on its polarization. Photons traveling through this warped space can split into pairs or merge together, processes that sound like science fiction but follow directly from well-tested quantum field theory. The implications extend beyond magnetars themselves. Similar physics might operate in other extreme environments we've barely begun to explore. The collision of two black holes, the surface of strange quark stars if they exist, or the cores of the most massive neutron stars might all generate fields approaching magnetar strength for brief moments. Each of these scenarios tests our theories in different ways, revealing whether our understanding holds up under conditions far removed from everyday experience. Magnetars also challenge our assumptions about stellar evolution. We thought we understood how massive stars end their lives. They burn through their fuel, collapse, explode, and leave behind either a neutron star or a black hole depending on their mass. This picture remains broadly correct, but magnetars add nuance. Not every massive star explosion produces the same kind of neutron star. Small differences in rotation, magnetic field strength, or binary interactions can push the outcome in dramatically different directions. The detection of fast radio bursts changed everything. These millisecond-long pulses of radio waves arrive from distant galaxies, carrying energy that seems impossible to generate through conventional means. When SGR 1935 plus 2154 produced a fast radio burst in 2020, it confirmed what many had suspected but couldn't prove. Magnetars can generate these signals, at least some of them, through mechanisms we're still working to understand fully. The discovery didn't solve the mystery completely. Some fast radio bursts repeat regularly, others appear once and never again. Some come from galaxies billions of light years away, others from relatively nearby. The diversity suggests multiple formation mechanisms might be at work, with magnetars representing one path among several. But having one confirmed source gives us a starting point, a known physics laboratory we can study in detail. What makes a magnetar produce a fast radio burst? The leading theory involves sudden rearrangements of the magnetic field near the star's surface, creating conditions that accelerate particles to extreme velocities. These particles emit coherent radiation as they spiral through the twisted field lines, producing the brief intense pulses we detect. The details remain murky. Field line reconnection, crustal fractures, or oscillations in the magnetosphere might all contribute, possibly working together in ways current models don't capture. Testing these ideas requires better instruments. Current telescopes can detect fast radio bursts and measure their properties, but they can't resolve fine details about their emission regions. Next-generation facilities now under construction will have the sensitivity and time resolution to catch the subtle variations that reveal underlying mechanisms. We're entering an era where these objects transition from mysterious phenomena to physics laboratories we can actually probe. The connection between magnetars and fast radio bursts also suggests something profound about the universe's evolution. These bursts travel across billions of light years, carrying information about the space they traverse. As the radio waves pass through ionized gas between galaxies, they disperse slightly, with different frequencies arriving at fractionally different times. Measuring this dispersion tells us about the density of matter along the line of sight, providing a new tool for mapping the universe's large-scale structure. Young magnetars might play another role we're only beginning to appreciate. When a massive star explodes, it doesn't just create a neutron star. It also drives shock waves through surrounding material, heating gas to millions of degrees and accelerating cosmic rays to energies that dwarf anything we can produce in particle accelerators. A newly formed magnetar, spinning rapidly and radiating enormous power, could inject additional energy into this environment, affecting how the supernova remnant evolves over thousands of years. Some superluminous supernovae, explosions that outshine their entire host galaxies, might be powered by central magnetars. The standard supernova mechanism, where the collapsing core rebounds and blows off the star's outer layers, can't explain the extreme brightness of these events. But a magnetar spinning hundreds of times per second could pump energy into the expanding debris for weeks or months, making it glow far brighter than ordinary supernovae. Observations support this idea without yet confirming it definitively. The magnetic field itself might contribute to the explosion. Simulations suggest that in rapidly rotating collapse scenarios, magnetic fields can channel energy outward along the rotation axis, creating powerful jets that punch through the star before the rest of it has time to explode. These magnetar-driven jets might explain certain rare supernova types that show unusual geometric patterns in their debris, elongated structures pointing in opposite directions rather than the roughly spherical shells produced by standard explosions. Each new observation refines our understanding while raising fresh questions. Why do some magnetars produce giant flares while others remain relatively quiet? What determines the initial magnetic field strength in the first place? Can we predict which massive stars will become magnetars rather than ordinary pulsars? The answers matter for more than academic curiosity. They tell us how elements heavier than iron form and spread through galaxies, how magnetic fields thread the cosmos, and what extreme physics looks like when pushed to its breaking point. The nearest magnetar sits 9,000 light-years away, far enough that even its most powerful outburst poses no threat to Earth. We're safe, at least from known magnetars. But the galaxy contains stellar nurseries where new massive stars are forming continuously, future magnetars waiting to be born. In a million years, one of them might explode relatively nearby, creating a magnetar we could study in unprecedented detail. Or it might have happened already, with the light from that explosion still traveling toward us through interstellar space. What we learn from magnetars feeds back into broader questions about the universe. How common are these objects in other galaxies? Do they contribute significantly to the mysterious high-energy backgrounds we detect? Could ancient magnetar flares have influenced Earth's atmosphere in the distant past, leaving traces we haven't yet recognized? Each question opens new research directions, connecting stellar physics to planetary science to cosmology in unexpected ways. The technology we develop to study magnetars often finds applications elsewhere. Detectors sensitive enough to catch their faint X-ray pulses can also track other high-energy phenomena. Analysis techniques that extract signal from noise in their burst data improve our ability to find gravitational waves or exoplanet transits. Theoretical tools that model their magnetic fields advance our understanding of plasma physics in fusion reactors and solar flares. Pure research rarely stays pure for long. Magnetars remind us that the universe operates on scales both incomprehensibly large and impossibly small, where city-sized objects generate magnetic fields that warp the fabric of spacetime itself, where quantum mechanics and general relativity both play crucial roles, and where the physics we've worked out in comfortable laboratories faces its ultimate test. They're not just exotic curiosities. They're natural laboratories pushing matter and energy to extremes we can barely imagine, revealing what's possible when nature stops holding back. Every active magnetar we know about will eventually fall silent. The magnetic field that defines them, that makes them the most extreme objects we can observe, decays over millennia until nothing remarkable remains. 10,000 years from now, the magnetars currently terrorizing their neighborhoods will be indistinguishable from ordinary neutron stars, spinning quietly in the dark, their violence spent. This creates a peculiar situation. We're living during a brief window when these objects are visible, when their youth makes them loud enough to detect across thousands of light years. The galaxy has hosted magnetars for billions of years, but we only see the current generation, the ones active right now. The rest are ghosts, invisible remnants carrying the memory of power they no longer possess. Statistical models suggest 30 million dead magnetars populate the Milky Way. 30 million objects that once commanded their surroundings through sheer magnetic force, now drifting through space contributing nothing but gravitational pull. They haven't disappeared. They've just moved beyond our ability to notice them, joining the vast population of stellar corpses that fill the space between stars. The ones we can study tell us something fundamental about how the universe operates at extremes. Physics textbooks describe magnetic fields using equations derived from experiments with bar magnets and current-carrying wires. Those equations work perfectly for everyday applications. They even work for most astronomical contexts, from planetary magnetospheres to the fields threading galactic arms. But magnetars exist at the edge of validity, where the equations themselves start showing strain. Near a magnetar, quantum mechanics and general relativity both become essential for describing what happens. You can't ignore either one. The magnetic field warps spacetime measurably. Quantum effects alter how light propagates through vacuum. The object sits at the intersection of physics regimes that normally operate independently, forcing them to work together in ways we're still learning to calculate correctly. This makes magnetars valuable beyond their intrinsic interest. They're testing grounds for theories we can't validate any other way. Want to know how matter behaves at nuclear densities under magnetic fields a quadrillion times Earth's? Find a magnetar and measure its emission spectrum. Curious whether quantum electrodynamics holds up when electromagnetic field energies exceed particle rest mass energies? Watch how X-rays propagate through magnetar magnetospheres. These aren't Gedanken experiments. They're real observations probing real physics in regimes laboratories will never reach. The connection to fast radio bursts transformed magnetars from obscure specialists' objects into key players in modern astrophysics. Before 2020, fast radio bursts were one of astronomy's deepest mysteries, bright millisecond pulses arriving from distant galaxies with no confirmed source. Multiple theories competed, some invoking exotic physics we'd never observed. Then SGR 1935 plus 2154 produced a burst, and suddenly we had an answer. Not the only answer, perhaps, but a confirmed mechanism that worked. This pattern repeats throughout science. A phenomenon appears mysterious until we catch it in the act, then everything clicks. Magnetars went from hypothetical to confirmed through patient observation and theoretical development. Fast radio bursts followed a similar arc. Now we're watching both fields mature, moving from discovery to detailed characterization, from asking, "What are these?" to asking, "How exactly do they work?" The answers will come from better instruments and smarter analysis, but also from luck. Magnetar giant flares are rare. We've observed 3 in modern astronomical history. The next one might happen tomorrow or might not happen for decades. When it does, having instruments pointed in the right direction with the right sensitivity to capture every detail could transform our understanding overnight. Or we might miss it entirely, left with fragmentary data from satellites that weren't designed for this purpose. Some questions won't wait for lucky observations. The theoretical work continues independently, pushing deeper into the mathematics of magnetic field evolution, crustal fracture mechanics, and quantum vacuum effects. Computer simulations improve year by year, incorporating more physics and running at higher resolution. Each advance reveals new complexity, new phenomena that observations will eventually need to confirm or refute. We're essentially trying to reconstruct the biography of objects that live fast and die young by cosmic standards. A magnetar's active lifetime spans 10,000 years, a blink compared to the billions of years typical stars enjoy. During that brief window, they experience violent starquakes, emit radiation that crosses galaxies, and demonstrate physics that nothing else in nature provides access to. Then they fade, leaving behind only their mass and gravity. Understanding this life cycle connects to broader questions about stellar evolution and galactic ecology. Massive stars create most elements heavier than helium through fusion and supernova nucleosynthesis. When they collapse into neutron stars, magnetars included, they remove that material from circulation temporarily. Eventually, given enough time, even neutron stars might decay through quantum processes, returning their mass to the universe in forms we can only speculate about. But that's trillions of years away, far beyond anything we can observe directly. In the meantime, magnetars continue doing what they do best, being dangerous, dramatic, and scientifically invaluable. Every burst we detect, every pulse we time, every spectrum we analyze adds another piece to the puzzle. The picture emerging shows a universe more violent and more interesting than we imagined, where dead stars can terrorize their neighborhoods for millennia and where the strongest magnetic fields in existence emerge from stellar corpses no bigger than cities. The galaxy contains wonders we're only beginning to catalog. Magnetars rank among the most extreme, pushing matter and fields to limits that seem designed to test our theories. They're not the only exotic objects out there, but they might be the most thoroughly hostile to anything complex enough to observe them. From 1,000 kilometers away, your atoms would deform. From halfway to the moon, your credit cards would erase. From 42,000 light-years, they can disrupt Earth's ionosphere with a single bad day. That's the universe we inhabit. One where stellar remnants command physics that shouldn't exist, where quantum mechanics warps vacuum into optical crystals, and where the brightest explosions since the Big Bang happen regularly in objects smaller than the island of Manhattan. Magnetars aren't comfortable. They don't fit into neat categories. They challenge our assumptions about what's possible. And somewhere out there, hidden in the stellar nurseries where massive stars are being born right now, future magnetars are waiting. Stars that will live brilliantly for a few million years before collapsing into objects we'll study with instruments that haven't been invented yet. The cycle continues, generation after generation, creating laboratories that test physics at its breaking point and reminding us that the universe operates on scales we're only beginning to comprehend.